Hi there, and welcome to the past paper questions 5 on all the past paper exam style questions that have come up on the bin packing algorithms in the Edexcel Decision 1 Maths module. Again, this would be very useful for many other decision maths modules in other boards. As always, if you need help with your maths studies, GCSE or A-level, see my YouTube channel HEGARTYMATHS or my website. Okay, let's take a look at the first question. June 2008, question 1, 8 marks in total. Pause the video, attempt the question, and then mark your work against my solutions as I go through. So in 10 seconds I'll go through. Pause now. Okay, let's go through this. Here are our numbers. The numbers in the list represent lengths in minutes of 9 radio programs. They are to be recorded onto tapes which can each store 100-minute programs. Obtain a lower bound. So for the lower bound, it's nice and easy, this one, lower bound. You simply add up the numbers. So you add up 29, 52, 73, 87, 74, 47, 38, 61 and 41. So you get 502 when you do that. So if you want to record them onto 100-minute programs, the lower bound is therefore 502 divided by 100. You get just over 5, so 5.02. So the lower bound is therefore you need at least 6 tapes, okay, as a lower bound. Okay, let's do the next part. The next part then talks about using the first fit bin packing algorithm to fit the tapes onto the shape. So first fit is simply as they come. So here's 100 for the first tape. So your 29 would certainly fit there. Your 52 would certainly fit there as well. Your 73 wouldn't, it would go on the next one. So your 73 would go there. Your 87 wouldn't fit on any of the two above. So your 87 would go there. Your 74 would not fit on any of the above, so it would go there. Okay, your 47, would that fit anywhere? No, 47 no good anywhere, so 47 goes on its own as well. 38, would 38 fit anywhere? Well, 38 wouldn't fit in any of these, but it would fit here, so 38 would nicely fit there. 61, would it fit anywhere? Unfortunately not, 61. And would 41 fit anywhere? Well, 41 would not even fit anywhere else left over here, so unfortunately 41 goes here. Okay, now we need 1, 2, 3, 4, 5, 6, 7 tapes. And as we can see, that is not very efficient. There's so much wasted space here, 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 a bit here, here, and here, and that doesn't look like it's a particularly good method. Okay, first fit decreasing. For the last one, first fit decreasing, let's put them in order from biggest to smallest. So biggest was 87. Okay, then we'd have had 74 here. Then we'd have had 73 here. Then we'd have had 61 here. Then we'd have had 52. Then we'd have had 47 and 41, 47, 41. Then we'd have had 38 and 29, 38 and 29. So they are in a decreasing order now. So let's try the same process. So first tape 100, the 87 would go there. Let's cross off our 87. Then the next tape of 100, well, the 74 couldn't go here, so it must go here. The next 73 couldn't go here, so it must go here. The 61, well, couldn't go here, or here, so it'd have to go on a new tape of its own. The 52, again, requires a new tape. The 47 now, couldn't go here, or here, but could nicely go here for us. The 41 next, couldn't unfortunately go in any of these, so would have to go in its own tape. The 38 could go here quite nicely, okay, and that would add up to 99. And the 29 here couldn't unfortunately go to any of these, but could end up here. So we've got 1, 2, 3, 4, 5, 6 tapes here, 6 tapes, and it seems a lot less wasted space. And hence we've done this question now and got an easy 8 marks relatively. Okay, let's move on to the next question, which is June 2010 question 3, 9-mark question. As always, pause the video, have a go through the question, and then mark it against my answers in 10 seconds. Okay, so we've got a list of weights here of 7 statues. They'd be transported in crates that can weigh a maximum of 60 kilograms. What's the lower bound? Well, obviously for the lower bound, as always, you just add up the numbers. So you add up the 41, the 28, the 42, the 31, the 36, the 32, and the 29. And you get 239. And you want to get that into 60 things, into weights of 60. So 239 divided by 60, that tells you 3.98. So therefore the lower bound is 4 crates. Nice, easy 2 marks there. Okay, next it asks us to use the first fit bin packing to allocate the statues to the crates. So simple here. The first crate I'm going to say is 60, so the 41 just goes in normally. The 28 would have to go, unfortunately, into its own one. The 42 would have to go into its own one. The 31, well, the 31 could nicely fit in here, so the 31 could go here. The 36, unfortunately, would have to go in its own one. The 32 couldn't fit there, but and couldn't even fit there, unfortunately, so the 32 would have to go here. And lastly, the 29, well, the 29 couldn't go here, here or here, unfortunately. So we've got 1, 2, 3, 4, 5, 6. So we've got 6 crates with a fair bit of wastage, okay? Okay, next it says use the full bin algorithm to allocate crates to statues. So all we're going to do is we're going to see if we can add things up so they approximately get to 60. So do any two things add to 60 that we can see? Well, 31 and 29 add to 60. So 31 and 29 fit nicely into a 60. Okay, 32 and 28 do as well. So 32 and 28 do as well. So we've done those. And anything left else, the rest unfortunately don't fit into. So the rest would unfortunately end up being on their own. So you'd have a 41, a 42 and a 36 left over. That done. And lastly it says explain why it's not possible to transport the statues in fewer crates than the number in part C. Well, if we look back at our original list, okay, how many items have we got over halfway? Well, that's over half, that's over half, that's over half, that's over half, that is over half. There are 1, 2, 3, 4, 5 things that are over half, okay, and over half significantly, and there are only 2 things that are under half, okay. So the fact that there are 5 things over half means that there would have to be 5 crates required to solve this problem. Okay, next question. Take a look. It's D1, January 2011. As always, pause the video, attempt the question, and then mark your work against mine. Okay, it asks us for part A to work out a lower bound. As always, you add the numbers up and you divide by how much is in each space here. So we're going to add these numbers up. We're going to add 23 plus 29 plus 11 plus 34 plus 10 plus 14 plus 35 plus 17 for the lower bound. And you get 173, and then you take 173 and you divide it by 50, and you get 3.46. So it tells you the lower bound is 4 discs. So that's the least the answer could be. Okay, next it asks us to use the first fit bin packing to fit the files on the disk. So this is simple as always. All you do is you take the first disk, which is 50, you fit that 23 on it. Can the 29 fit on it? The 29 couldn't fit on it, it would be too big, so the 29 has to go on its own. That was 23, that should have been. Okay, where could that 11 have gone there? Yes, the 11 could have gone there. Where could that 34 go? Not here, not here. So the 34 would have to go on its own. The 10, well, in total, this is adding up to 34. So that 10 could nicely fit on there. That 14 could actually nicely fit on here. This 35, unfortunately, would have to go to another disk. And the 17 at the end, well, the 17 couldn't fit here, okay, but here we've got a total of 39 and 43, so this 17 could actually, that would be 43, so couldn't fit there, and couldn't fit there either, and unfortunately couldn't fit there either, so this 17 would have to go on its own. So we've got 1, 2, 3, 4, 5 discs required with lots of space left over. Okay, next it wants us to perform a bubble sort on the numbers in the list to make them in descending order. You only need to write down the result of each pass. Okay, so we're going to do a bubble sort on these numbers here. Let's write them down. 23, 29, 11, 34, 10, 14, 35 and 17. Okay, now for a bubble sort, you compare the first two. You want to put them in descending, remember, so you want big going to small. Compare the first two, need a swap. 29 goes there. Consider 23 and 11, keep the 23 as it is. 11 and 34 need to swap. 11 and 10 keep the same. 10 and 14 need to swap. 10 and 35 need to swap. And 10 and 17 need to swap. So 10, the smallest number, ends up on the end. Let's keep going. No swap required. Here we need to swap 34. 23 against 11, 23 stays. 11 against 14, 14 comes in. 11 against 35, 35 comes in. And 11 against 17, 17 comes in. And 11, the second smallest number, ends up going to the back. Okay, compare these two. Need to make a swap. 29 with 23 keeps there. 23 with 14 stays there. 14 with 35 need to make a swap. 14 with 17 need to make a swap. And the 14, the next smallest number, ends up there with the 11 and the 10. Okay, these two, no need to make a swap. These two, no need to make a swap. These two need to get that 35 moving forward. The 23 against the 17, no need to make a swap. And the 17 is confirmed as the next smallest number. Okay, no need to make a swap here. Yes, we should make a swap here. 35 goes there. 29 against 23, no need to make a swap. And 23 is confirmed as the next smallest number. Okay, and here we do need to make one final swap. So the 35 goes there, the 34 goes there, and 29 is confirmed as the next smallest. But remember, with the bubble sort needs to run through the algorithm once without having a swap to know it's finished. So it has to go through one more time, and without making any swaps there, it knows it's finished. and hence you have the numbers in descending order as required in the question for 4 marks. For the last part, you use the first fit decreasing to try and fit them in. So let's have a go. They are from part C in decreasing order. So the first 50, the 35 can go in there. The 34 must go in its own one in here. Okay. The 29 must go in its own one. Okay, the 23 now, again, unfortunately, must go in its own one. Now, the 17 can't go here, but can go here nicely, because that would give us a total of 46. This 14 could, in fact, go here. There's space for it here. The 11 could then slot in here, and the 10 could slot in very nicely in here. So we've got 1, 2, 3, 4 discs used here, and a lot less wasted space. And so that's the answer to the January 2011 past paper. Okay, then we've got our another question here, our last past paper. So as always, here we go. Take a look. It's January 2012. Pause the video. In 10 seconds, I'll work through the solutions. You mark your work. Okay, the question is asking us to use the first fit bin packing algorithm to determine how many numbers listed above can be fitted into bins of size 20. Okay, so let's write our bins out. Here's my first bin. That 5 will go in there nicely. That 1 will go in there. The 8 will also go in there. But the 13 now is too much, so the 13 would have to go in its own one here. The 16 would have to go in its own one. The 5 actually could fit in the top one here. The 8 here could not fit here nor here, so the 8 would have to go here. The 2 could fit in this one. There's no space for it here, but it could fit here. The 15 could fit nicely into, well, no, the 15 would have to go into its own one, apologies. The 12 couldn't fit here, but the 12 could nicely fit into this one, and the 10 couldn't fit here, nor here, nor here, nor here, nor here, so the 10 would have to go into its own one. So you'd need 1, 2, 3, 4, 5, 6. So you would need 6 bins of size 20. As described in this example here. Okay, next one here, the list of numbers is to be sorted in descending. Use the bubble sort to obtain a sorted list given the state of the list after each complete pass. Okay, so we're going to have to do a bubble sort here. So write the numbers out. They're 5, 1, 8, 13, 16, 5, 8, 2, 15, 12 and 10. Okay, so we compare the we're going to do them in descending, so we want big to small. Okay, compare these, keep them where they are. Compare these, need to make the 8 there. Compare these, need to make the 13 there. The 16 needs to go here. The 5 here. The 8 here, because the 1 is travelling all the way to the back. Okay, the 2 here. The 15 here. The 12 here. The 10 here, and the 1. The smallest always goes to the back, okay, in this case. Now, the next smallest is going to be 2. That's going to end up in the back. Let's go through the process. Do we need to make a swap? Yes. 5 and 13? Yes. 5 and 16? Yes. 5 and 5? No. 5 and 8? Yes. 5 and 2? No. 2 and 15? Yes. 2 and 12? Yes. 2 and 10? Yes. And the 2, the next smallest, ends up in the back. Okay, next, do we need to make a swap? Yes. 8 and 16, yes. 8 and 5, no. 5 and 8, yes. 5 and 5, no. 5 and 15, yes. 5 and 12, yes. 5 and 10, yes. And 5, the next smallest number has made its way to the back. Now this 5 is going to make its way to the back. Here we compare these two. Need to make a swap, yes. Need to make a swap, no. No swap with 8 and 8. No swap with 8 and 5. Yes, a swap here, 15 here and the 5 here. 5 and 15, yes, a swap. 5 and 10, yes, a swap. And the next smallest number, the 5, has now made its way to the back here. Okay, now compare these, no need to swap. Compare these, no need to swap. Compare these, no need to swap. Compare these, need to swap. Compare these, 8 and the 12 need to swap. Compare these, 8 and the 10 need to swap. And the 8, the next smallest, ends up going here. Okay, keep going, no need to swap, no need to swap, need a swap, need a swap, and need a swap, and the 8, again, the next smallest, ends up at the back where required. And we're getting close now. No need to swap, yes, a swap's required, no need to swap, no need to swap. And we've got our 8, our 8, our next smallest must be the 10, our 5, our 5, our 2, and our 1. And lastly, if we went through a whole pass here, we'd realise there's no swaps, and that's what the algorithm needs to do. It would go through the whole lot, realise I haven't made a swap, and therefore I have completed putting these into descending order as was required of me. Okay, and next we're going to move on to part C. It says apply the first fit decreasing. Well, they're in decreasing order, so let's have a go at doing this now. Okay, this 16 would fit in here. This 15 would have to go into its own 1. This 13 would have to go into its own 1. This 12 would have to go into its own 1. And this 10 here would then have to go into its own 1. But this 8 could fit there. This 8 could fit there. This 5 could fit there first of all. This 5 could then fit there. And this 2 could fit there, and that 1 could fit there. So we need 1, 2, 3, 4, 5. We need 5 discs, and there's a bit less wastage. And the last one says for us, determine whether your answer uses the minimum number of bins. Well, what I would do for part D is work out the lower bound. The lower bound is the sum of all these divided by 20. So that would be equal to 95 divided by 20. And I get for that, when I do that, 4.75. So the lower bound must be 5. Therefore, so yes, it is the minimum because it equals the lower bound. And that's it, we're done. That's all the questions done on the first fit and the bin packing algorithms that come up in Decision 1 Maths. I hope you found the following useful in your revision for D1. Please tune in for the next video tutorial to help you through your Decision 1 course. Thanks for watching.